Okay, welcome everybody. Let's get started. So today I'm going to finish what we were talking about before, which is an overview of different Fpga architecture styles. And then we're going to go deeper into how you build an Fpga, into some of the low-level Fpga circuitry. And time permitting, I'm also going to talk a bit more about the brainwave paper that we covered last week, just because it's a pretty interesting paper. Okay, so background reading last week was on logic block design. We're not going to get all the way to that one this week, but we will next lecture after this one. The assigned reading for this week is also on logic architecture. So basically, what the Stratix 2 architecture from Altera, because this brought in a major change in how logic architecture was done that most subsequent FPGAs have adopted, something called the fracturable lookup table. So a bit more complicated than the lookup tables we'll look at today. Okay, so we were talking about FPGA architecture styles. We didn't quite finish that last week. So I'm going to go back and using the good version of OneNote. So the Windows 10 version. Hopefully this will be a little easier to use. Yeah, let's see. I'm reminding myself of where we left off. Okay, so we talked about different logic structures, and we talked about how lookup tables have become dominant, and no logic structure it kind of scales to very large sizes. You're going to have to combine a lot of logic elements together with some kind of routing architecture to make a big chip. We looked at hierarchical FPGAs, which were designed to kind of mimic the hierarchy that hardware designs have. And we saw that they have some strengths, but they have a pretty significant disadvantage. They don't scale to really big chip sizes because you start getting these really long wires to become highly resistive. So the other style of FPGA that people look at are these island style FPGAs. And those were, let me move this up a bit. Okay, so what we were talking about were these island style FPGAs. And I drew you a little picture of this last time. I'll just draw it quickly again. Okay, so we have logic blocks laid out in a two-dimensional grid, and in between them are routing tracks. So routing wires that are prefabricated. They have a certain length before they end, and they use programmable switches to connect them together into longer routes that let you get further. Okay, so finish drawing this out. And change my color here. So let's see if I can do that properly. So there are programmable switches that let you connect from blocks, block inputs and outputs to these wires. And I'm showing those with X's. And then there are programmable switches that let you connect the wires to each other. So I'll draw those as kind of dashed purple lines. So when a wire ends, you have the option to go through a programmable switch and go further. You might also have the option when a wire doesn't end to use a programmable switch to connect to a different wire. So there's a bunch of programmable switches like that. And this structure, really repeats. So I've shown a tiny piece of an island style FPGA. Okay, so what are some of the, just move this picture. Okay, so what are some of the important properties of this? So we have routing channels that surround logic blocks. Okay, so a routing channel is basically, that would be a routing channel. That would be a vertical routing channel. So it contains more than one routing wire. Okay, so inside these routing channels, they're filled with wire segments. Okay, so everything has to be prefabricated in an FPGA. So we've basically, let's see if I choose the color here again. There we go. Let's see. So basically, this would be a single routing segment right there. And this would be another routing segment there. Usually we have several different segment lengths. So we prefabricated them to give ourselves more options. We'll probably build different wire lengths, maybe some short, some long. And here I've drawn a couple different types. Whoops. Go back there. Right, so I've got a length 1 here. I've got a length 2 one here. So we've got different lengths of wiring. And we usually talk about these lengths in terms of how many logic blocks they span before they end. So 1, 2, maybe 8, etc. logic blocks. In this little piece of an architecture, you can see wires that are of length 1. So again, it's this one over here. It only goes one unit over before it ends. And we've got some wires of length 2. So that's this one here, which goes 2 blocks up or down before it ends. Okay, so that can't get us too far though. And doesn't get us in diagonal directions. So we also need programmable switches. Okay, so we got 2 types of programmable switches. We've got programmable switches to connect the wires to the logic block inputs and outputs. And that's given the name connection box. Okay, so let's see if I can get a good highlighter here. So basically these X's here and here, those form a connection box. So we draw a box around that and say that's a connection box. We have another kind of, programmable switch, which is to connect routing wires to each other. Okay, and we call that a switch box. Or sometimes people call it a switch block. And let's see, that is basically these switches here. So those programmable switches that go between different kinds of wires are called, together they form a switch block or switch box. Okay, the last important thing is the channel width. This important piece of, well, I'll write it here. So the last piece of terminology is the channel width, which we give the symbol W, and it's number of wires in a channel. Well, or number of wires, let's say across a channel. So for example, on this, that would be one channel. And here's a test to see if people are getting this notation. What is W? So it's the number of wires across the channel. For the channel I just showed you, what's W? Just type it in the chat, or you can unmute yourself and speak up if you are very brave. Yeah, so it's 2 wires, okay? So in this case, W equals 2 in this example. Okay, so that's defining some terminology and the basics of what is this island style FPGA. And again, the key insight behind an island style FPGA is that we're building things on a 2D piece of silicon, so we can connect things we can make efficient two-dimensional structures. We can make wires and switches in this kind of 2D layout, and we can build it efficiently. So now the question is, can circuits use that efficiently or not? Okay, so a positive of this architecture, I guess if we contrast it to the hierarchical FPGA, because this is really kind of based on physics. We have a two-dimensional substrate, we can build a two-dimensional pattern on it. It fundamentally means that physically close blocks can be connected with fast routing. We can build an architecture where, yeah, if things are close together, we can connect them with short wires, not many programmable switches, not many wires connected together, so we can have a fast routing. And remember, a hierarchical FPGA didn't always give that to us. We had some things that could be close together on the chip where, because they were still far apart in this hierarchical FPGA interconnect, they might take a long time to connect. And an island style FPGA, if you design it well, that's not going to happen. Now we still have some connections that are going to have to go a longer distance. So what about them? And the way island style FPGAs handle those longer connections is that they build these longer routing wire segments. So longer wires or longer segments. I'm going to use that those terms somewhat interchangeably. So that means if we build some longer wire segments, then far away blocks, far apart blocks still have something reasonable. Definitely closer to be better, but we can make some reasonable pattern. Okay, so that's one positive. Let's see, I think this might be too hard to guess, people. So I guess we did a big analysis of how scalable a hierarchical FPGA was. And we showed that because circuits have locality, which we can express by their rent exponent. If you have a low rent exponent, you've got a circuit that has very local communication. A rent exponent approaching 1 means your communication is not very local. So this is actually probably a hard one to answer, but basically it turns out that island style FPGAs are also scalable. Hierarchical FPGAs benefit from locality. It's part of what makes them work reasonably well. But we saw as you get to really big designs with resistive wires, they don't scale that well. Okay, island style FPGAs are pretty scalable. They scale well to big designs. And to show that, I'm going to do a rinse rule analysis, just like we did for hierarchical FPGAs. So let's consider an M by M. Okay, so I just made an arbitrary variable M. I'm going to make an M by M array of logic blocks. Okay, so let's draw that out. So we've got logic blocks, and I'm defining, the length of the one side of this array to be M logic blocks. Okay, and I'm just going to draw a box around that. That's the amount of logic that I'm considering. Okay, so I want to compare how much logic I've put inside this box to how much wiring is coming out of it. Okay, so I've got routing channels. Let's see if I can use some different colors here. So I've got routing channels here. So this will be a routing channel, and this will be another routing channel. And I'm going to have also vertical routing channels. So I'll have a routing channel here, and I'll have another routing channel here. Okay. Basically, this is my repeatable structure. Every logic block comes with a routing channel above it and a routing channel to its right. And if I keep repeating that, I would eventually stamp out an arbitrarily huge FPGA. So this is my basic pattern. Okay, so I want to compare my logic to my routing demand. So the amount of logic in this is pretty easy. So logic in an M by M array is just M squared. Okay, now I want to know how much wiring I have, wires leaving or entering this. Okay, so I want to know how much wiring I have, on the edges here. If I add all these wires up, how many are there? Okay, so how many, if my channel width is W, okay, so we said the number of wires per channel is W, so W wires per channel. Okay, so my answer of how many wires are leaving this M by M array, let's put the other M on here to make clear what it is. Okay, every one of these channels is going to have W wires in it. Okay, so my answer is going to have a W in it. What's the rest of the answer? How many wires are going to leave this area that I put a dash box around? Okay, to physically leave it. How many are built on the chip? So if anybody's got an idea, and I've already given you that it's going to have a W in it because every one of these channels has W wires. If you feel you know the answer, just type it in the chat. So it's going to have a W. It's going to have some function of M. So 4 times W, M times W, very close. If KP and Marius put their answers together, they're there. So we've got an M squared times W. So we've got many things that are close. Okay, so Iggy got it and Marius got it as well at the same time. So yeah, I've got 4 sides. So that's my 4. And Andrew, can you see my cursor when I put my pen close like this or not? I guess you can't. Okay, so I got to make sure I draw. No. Okay, that's useful to know. Okay, so I've got 4 sides, right? So there's my side 1, 2, 3, 4. So that's where the 4 comes from. And then the number of routing channels on each of those sides is M. So I've drawn a 2 by 2 array here. And so if M equals 2, I have 2 routing channels. If M was 3, I'd have 3 and so on. And then the number of wires in each of those routing channels is W. So 4MW is the amount of wires leaving. Okay, I'm going to define that just like we did for the hierarchical FPGA. We said there was a certain routing supply. This is our wiring supply. That's what's actually on the chip. Region that has M squared units of logic has 4 times M times W wires going, crossing its boundary. So we can use that to connect up terminals. All right, so we now need to compare that to what Rent's rule says we're going to need. So Rent's rules, remember, says the number of terminals going into some cluster or group of logic is equal to some constant times the amount of logic, which Rent wrote in terms of gates, to the Rent exponent, P. So this exponent between 0 and 1. Okay, so if I can just rewrite that, C is an arbitrary constant, so I'm just going to make it a new arbitrary constant, C prime. And that's going to let me change my units of logic from gates to basically logic blocks. And the number of logic blocks I have is M squared. Okay, so that's my total amount of logic. So all I've done here is I basically replace the G with some constant times M squared, right? My amount of logic is proportional to M squared. And I now need to put this P back in. Okay, because all I did was substitute in for G. Okay, so I can rewrite that to be slightly more simple as M squared 2P. And that's how many signals want to go in or out of this block of, M squared, or this group of M squared logic blocks. So we can call that W demand. Right, that's what the circuit needs. And this is what the circuit supplies, or the architecture supplies, W supply. And to successfully route, we need W demand, what the circuit needs and wants, to be less than W supply, what the actual FPGA provides. Otherwise, your CAD tools are going to say, I can't route it. I ran out of wiring. Life will be hard. Okay, so we want W demand to be less than W supply. So when will that happen? So we're just going to plug in the numbers. W demand was C prime times M to the 2P, right? This is what we wrote above. And we wrote that W supply is 4 times MW. So we can just do a little bit of manipulation here. So we divide by 4, we get C prime divided by 4. We divide by M, so we get now M to the 2p minus 1 on this side. And that has to be less than or equal to W, because that's all that's left. We divided by 4M, and that's what we get. So what does this tell us? Well, it's easiest to see if we put in some examples for this rent exponent P. So if P is less than or equal to 0.5, we saw last week, those correspond to circuits that have good locality. Okay, if we had a linear chain of processing elements, the rent exponent was 0. If we had, and that some FIR filters can actually achieve that, or again, a linear pipeline. If we have a two-dimensional structure, so we make some kind of mesh or some kind of block of RAM, that has a rent exponent of 0.5, okay? And if our rent exponent is 0.5 or less, then this, this W demand term doesn't grow, okay? It doesn't grow with M because 2 times P minus 1 would be 0, okay? So we'd have no increase in the amount of wiring demand as the circuit got bigger. As the circuit gets bigger, M gets bigger, so we get more logic. Okay, so this is a very happy case. So if the rent exponent is less than 0.5, we're okay with a constant W. Okay, which means that we can keep making bigger and bigger FPGAs just by replicating this basic unit of a certain logic block and a certain number of routing wires that comes along with it, and it'll continue to route no matter how big we make it. We can make it 100 logic blocks, 1,000, 1,000,000, 1,000,000,000, whatever we can fit on the chip, and it's always going to route. So that's great. Okay. So for circuits with good locality, island style FPGAs are extremely scalable. Just keep stepping out the same pattern of logic block and routing, and they route fine. But obviously, rent exponent of 0.5, it definitely exists. It's not that rare, but they're nice circuits. There are lots of circuits that have higher rent exponents, and I talked about random logic, so finite state machines, lots of complicated control, can be more like 0.75. Okay, so if I plug in what happens if I put rent exponent of 0.75 in here, then, well, let's just do it. Then basically we'd have C prime over 4 M to the 2 times 0.75 minus 1, which is equal to this constant M to the 0.5. Okay, and that still has to be less than or equal to W. So that means that our W has to be made proportional to the square root of M. Okay, so for a circuit like this, rent exponent 0.75 tends to have more long distance communication. As we replicate more and more logic blocks, make a bigger and bigger FPGA, we are going to have to widen the channels. So we'd rather not do that, but we have to. But this still isn't too bad because the amount of logic is proportional to M squared. So that means that the square root of M is therefore actually proportional to the number of blocks in the design, in the circuit, to the 0.25. Okay? So that means that as we increase the number of blocks we build on the chip, we make a bigger chip, we do have to widen the channel if we want difficult circuits like this to route. But the growth is relatively small. Well, relatively controlled. It's the fourth root. So if I make something with, we'll see how fast I can do fourth roots in my head. If I make something with 10,000 times the logic, which is a lot, I have to make the channels 10 times as wide. So that's significant. 10 times as wide a channel is more area for sure. So your area per logic block plus the associated routing has gone up quite a bit. But you did increase the capacity of the chip by 10,000 times, and you only had to increase the width of the channel by a factor of 10. So it grows pretty well. So the key thing is that the channel width doesn't have to rise very rapidly. It's a slowly growing function. If you decided that you only wanted to route circuits with very good locality, these ones with rent exponent less than 0.5, you don't even have to change your channel width. If you want to do better than that, and you probably do, then you're going to increase your channel width, but you can increase it quite slowly. And in practice, a rent exponent of 0.75 is pretty bad for the whole circuit. The whole circuit probably isn't a rent exponent of 0.75. So it's rarely rent exponent of 0.75. There might be parts of it, like the control logic parts that are. But if only parts of it have a rent exponent of 0.75, a CAD tool can space out only those parts. Which basically means you can mitigate this growth in channel width a bit more. If your CAD tools are smart and the circuits are not so hard, then you can grow your channel even a bit slower. So what this means is that W is nearly constant. It's not quite constant as this logic array grows. But there's a big caveat. You need to have good placement. If your CAD tools basically scatter the logic around so that you get a lot of things that you need to connect to distant parts of the chip, then you're going to need much, much wider channels. So this means a low rent exponent means that a placement exists where the wiring is quite short. You have mostly local communication. You don't have that many connections going out of a block of logic. But if your CAD tools aren't very good, they won't find that placement. They'll do worse, and your rent exponent will appear higher. Okay, so you need good placement. I think everybody knows what placement is, like just the CAD phase that chooses, where do I put all the circuit elements that your design needs on the chip. The fact that W is very slowly growing, so it's good for scalability. It's also good in a practical sense for island style FPGAs. So I go back up here. This island style FPGAs, what most manufacturers do is they try to create a basic unit of logic, the logic block and the associated routing, and they make a tile for it. So they make a very highly optimized layout of the unit of the chip that I just drew a circle around, and then they stamp that out over and over again. Making a really optimized layout of an entire FPGA logic block and all the wiring that goes along with it is actually quite time consuming. So this will take many person years of effort. So they'd rather not change the channel width very often, because if I change the channel width, and I make it wider, not only do I lose efficiency, I actually have to relay out this basic block. So what FPGA manufacturers normally do is they make a whole family of FPGAs targeting a certain process node. So if you take Xilinx's latest chip, Versal, they're targeting a 7 nanometer process node with that. And they've chosen some channel width, and they'll make chips that vary in logic capacity by about a factor of 10. So they'll make some little chips, and they'll make some medium ones that are maybe 3 times that capacity, and some really big ones that are maybe 10 times that capacity. And they really don't want to redo the layout, because creating this layout for this basic unit was very expensive. They're going to have to redo it when they move to the next process technology. So that's okay. If they make a 5 nanometer FPGA, it's going to have to be redone anyway. But they'd rather not lay it out multiple times at the same process node, like 7 nanometers, for different size chips. And W grows slowly enough that you can basically just set W to be good for the biggest chips. Maybe it puts a little pressure on the CAD tool, and then just use that. And the smallest chips pay a small tax, but it's cheaper than relaying everything out. But you can only do that because it doesn't change very quickly. Okay, so that's some positives of island style. The negative is also kind of implicit in these positives. It needs good placement. Okay, so if we have a random placement, so our placement tool is really bad. It just basically scatters things in the first puts things down in the first legal spot. So it takes a logic block in the net list, of your design and just picks a random logic block on the chip, the rent exponent is approximately equal to 1, okay, which is really bad. And then W would grow much faster and you would run out of routing. And the chips also would not scale to very big chip designs. So you need good placement. Also, the routing architecture is relatively complicated. There are many routing choices. We basically just made a mix of short and long wires with some complicated switch pattern letting us connect them. So in a hierarchical FPGA, if you knew where you wanted to go, there was really just a very limited set of choices of how to get there. It was fairly obvious you need to cross this many hierarchy levels, so you're going to use these kinds of wires to do it. In island-style FPGAs, it's not nearly as obvious. You can construct all sorts of different combinations of short and long wires and switches being on to get from A to B. So that means you need a better routing tool. So you need a good routing tool, and it needs to be timing driven. So does everybody know what timing driven means? Does anybody want to define what timing driven is? So once again, just type in the chat or feel free to shout it out. So placement is optimized for best timing. Yeah, so it means literally optimized for timing. It can be applied to any phase of the CAD tool. So a timing driven router means that the routing algorithm is timing driven. Generally said, yeah, make sure the routing critical path is routed for priority, with priority, prioritize performance over area. So yeah, these are all correct. In an FPGA architecture like this, yeah, basically the router, which chooses how to get from this spot to some other spot over here, has a lot of choices, and even more, it has many choices if I'm trying to go a long distance, like way over here. And so it needs to prioritize timing. If that is, it needs to identify basically if the connection that I have to route from here to there, is that actually speed critical? So it needs to do timing analysis to figure out, is this going to limit my circuit speed if I do a bad job or not? If it might limit my circuit speed, then I want to make sure that I get priority. So that's correct. Give me the best wiring. But then also what the best wiring is depends on exactly where I'm trying to go. So even if I have priority, there are many choices of short and long wires and how I can connect them together. So I still need an algorithm that's fairly clever that connects a fast route to go this exact distance. So timing driven routers are significantly more complicated than routers that don't have to worry about it. They just try to connect you up in some legal way. And that's mixed in with, I guess it's driven by the fact that there's more diversity of routing choices than in a hierarchical FPGA. Okay, and we're going to look at the primary kind of architecture we're going to look at and try to optimize is island style. So we'll look at a bunch of these trade-offs. Okay, the last thing that we can do, which I think someone guessed at last week, is a hybrid. Can we combine the best of both these worlds? Okay, so hierarchical, just to re-summarize what its advantages were. Hierarchical had the advantages of simpler CAD, computer-aided design, but it had the disadvantage of poor scalability. Right, it had long wires, which are not scaling well with process technology, and had this annoying feature that the amount of interconnect bandwidth between two different parts of the hierarchy we had to choose when we made the chip, and some circuits might not like that choice. They might not need so much interconnect, or if they need more, then we had to space out a lot. So fixed interconnect bandwidth. Okay, so how could we combine hierarchical and island style? Maybe it's kind of obvious because I told you hierarchical. I guess there's two ways we could do it, right? We could do island style for little parts of the chip and then hierarchical to combine the big parts, or we could do the opposite. We could do hierarchical for little bits of the chip, kind of local regions, and then use island style routing to combine those little hierarchical FPGAs. And based on the advantages and disadvantages of hierarchical, that makes a lot more sense to do the latter, right? So we're going to use hierarchical. I am not spelling hierarchical properly. So okay, so use hierarchical at the lowest level of hierarchy. So make little hierarchical FPGAs basically. Okay, so our wires are still short, which we saw, well, sidesteps all those issues with resistance and so on. So what we can do is we can group what are often called basic logic elements. And that's what the reading that you had this week called them, into bigger things, which are often called, well, they're called logic blocks or logic clusters. Okay, now we have, our logic blocks now are basically bigger. Each logic block is not just one logic element like a lookup table and a flip-flop. It's a bunch of them grouped together with essentially local interconnect. So it's like a small hierarchical FPGA. Okay, and then we use island style right in between those. Okay, so what do these look like? So basically, we've got these BLEs, and a BLE is typically just a lookup table and a flip-flop. So it's a small logic element. And I make a few of those. Okay, and this is a whole bus. Commonly, there are n of these things. So we just define that as the number of BLEs. Okay, so each of these things has got a register in it and a lookup table. That's the most common logic element. So we take a clock should go to each of these things. Their outputs can go out to the general routing, and they can also feed back here to go back into these logic elements. Okay, and you can programmably choose, do I want to take some output and connect it back to the input of somebody? They also need to get inputs from the outside world. So there are inputs. We give them usually the symbol I, number of inputs. Whoops, that's a very messy I. Let me try that again. Okay, so some number I comes in of inputs, and we can also programmably connect to those. Okay, so make this a bit fatter. Okay, so this is a whole bus. So that's a bus, and this is a bus. Okay, so those are bigger than the other things. Okay, so this is basically called, this is local routing. The combination of these wires coming in from the outside and being distributed, and these local feedback wires and this programmable switching constitutes local routing. It's commonly built out of muxes or some other crossbar-like structure. We have a clock coming in here. And in this case, I've shown that clock just directly goes to every one of these basic logic elements, feeds the register in every single one of them. And I guess an important thing to draw is the boundary of this logic block. So I put this is basically the logic block. So that whole structure, becomes the logic block in an island style FPGA where we now make an array of those and we put these wires in between them and so on. Okay, so that's our, this whole small hierarchical FPGA, now goes into a logic block that we can replicate with island style routing to make a much bigger FPGA. Okay, so what is this good for? So why do we do this? And this is commonly used. So this is dominant in the chips that we're going to look at. So there must be some positives. So can anybody think of any positives? I'll even show you it again so you can look at it. Why would this be good? What is this doing for me? It does a few different things. I'm sure someone has an idea. They're probably typing it in the chat right now. So does this do anything useful for us in terms of hardware efficiency, speed of our hardware? Does it do anything to our CAD tools that we like? Why would I do this? Good communication between BLEs and a logic block. Yeah, so the local routing is fast. This local routing is basically built, I'm showing it as programmable switches, but it's basically built as muxes. And for these, this is actually faster than going through island style routing, which typically requires, you go out to a routing wire with a programmable switch. You may connect that to other routing wires with programmable switches. You have another programmable wire to connect to an input of a logic block. It's somewhat slower, even for very local connections, than this local routing, which can be done with just a single multiplexer from input to output. So the local routing is fast, so long as I don't make the clusters too big. So its local routing is fast for small to medium clusters. So what's that range? It's no completely fixed range. Maybe around 4 to 20 basic logic elements, and that's what the reading for this week was looking at, is what size of logic block makes sense. Clearly, if you made these clusters, 10,000, then the local routing becomes really slow due to all the issues we talked about for scalability of a crossbar. But for small ones, it's good. Okay, so any other, let's see, any other advantages? Yeah, avoid the long wires in the higher level of hierarchical. So yeah, it avoids the weakness of hierarchical architectures by not going on to, by not scaling to those really big ones. Any other advantages versus a vanilla island style though? Okay, so we've got one advantage. We actually have sped up our island style architecture by putting in this local routing for really local connections. What does it do to my CAD tools? You think this makes CAD tools easier or harder to write? And let me refine that, not just to write them, but to make them run well. So, because you might say, if I want to write the easiest CAD tool, maybe I want a 2-input lookup table as my logic block. But if I want it to actually run well for really big designs, is this going to help me or not? So I'm giving you a big hint, so I'm just going to go ahead and answer that one. So it does actually simplify the CAD flow. Okay, so basically we can do a CAD step called clustering. So we can do cluster. We don't have to do this, but we now have the option to do this. Clustering is basically a bottom-up partitioning. Okay, so I talked about partitioning, and that partitioning CAD tools tend to be quite good. So partitioning tools take, a blob of logic, like a big blob of logic, and they'll cut it in half. And then you might cut the halves in halves and so on. Clustering is really the same problem, but you attack it with a different algorithm. I don't want to take this blob of logic and cut it into 2 pieces. I want to cut it into maybe 10,000 pieces. And when you're going to cut it in 10,000 pieces, it's often better to do what's called clustering, which basically tries to gradually glue things together to make bigger pieces. So instead of cutting up cutting in halves and then quarters and so on. It'll instead look at the little things and start gluing them together because it wants to make 10,000, instead of having 100,000 little things, it wants 10,000 medium things. And clustering can be quite good at that, where it glues together the little things instead of chopping up the circuit into smaller and smaller parts till you got it chopped into 10,000 parts. And clusters work pretty well too. So we can cluster or do this bottom-up partitioning to logic clusters. Okay, so we can do that before we do placement. If we do that, we get a smaller placement problem. Basically, instead of placing 100,000 little things, we now have to place 10,000 medium things. That's still quite a few things to place, but it is, it's smaller. So we can cut the size of our placement problem by 4 to 20 times, which can speed up our placement engine. And placement tends to be the most difficult and most time-consuming part of the FPGA CAD flow. So speeding it up is very useful. For large FPGA designs, the CAD flow takes hours to even sometimes days. So it is an issue, and the issue is for the biggest chips. So if we can shorten this, this is good. So I have a question though. So if I decided that clustering is a good thing, do I really need to make these more complicated logic blocks, or could I just use clustering in my CAD flow to help placement no matter what? Whether I decided that whether I have actually these logic clusters in my architecture or not. So what do you think? Could I just have an island style FPGA with really small really small logic blocks? Each one's like a basic logic element with island style routing in between them, and so on. And I'm not drawing most of this, but let's say this is a really big chip with lots of wiring and so on. Could I use clustering even though I don't actually have these logic clusters? What do you think? This is one of those yes or no answers. So if you've just been waiting for a chance to guess, you got a 50-50 shot on this one. Okay, so several people are saying yes, you could, but it's not universal. Some say no. Camilo is saying you could, but then given the small number of wires needed to out of logic clusters, there's also lots of waste. So yeah, the answer is I could do this, right? I could just basically tell my CAD tools, let's pretend that these 4 basic logic elements are a cluster. And let's pretend these 4 are a cluster. And let's pretend these, well, I didn't draw them all, but basically, let's pretend various groups of say 4 basic logic elements are a logic cluster. Let's group logic together until we've got 4 basic logic elements in each one of the clusters we just made. Let's place those on essentially a coarsened grid. And then maybe we'll fine tune it after. And that's a perfectly reasonable thing to do. Okay, so could get some of these benefits. Even if the architecture doesn't have a logic cluster. But it is harder because we don't, basically we're trying to pretend, right? We don't really have such simple local routing. Let me just basically zoom in on one of these again. If I zoom in on one of these clusters that I just made, the local routing is really still a more complicated island style routing. So I can't necessarily guarantee that I'm going to get a fast route. It's a little more tricky to model what's going on. So I'm creating an abstraction to help my CAD tools. The abstraction is not quite true. It might still help the CAD tools, but it is going to be harder. Because basically the abstraction, isn't as true or accurate. Okay, any other positives? And let me give you a hint. Look at this clock. Okay, so the regular inputs that are going to the lookup tables and the data inputs of the flip-flops and so on, they come in on this set of regular routing wires, okay? And we have some local routing here. So we got muxes and so on that allows us to choose how to connect those kind of various signals up to the inputs of our lookup tables and the inputs of our flip-flops. But this clock, I drew this clock differently. The clock, I just show one clock coming in and it goes to every single one of the flip-flops in the whole logic block. There's one flip-flop, for example, in the BLEs I'm using. And I didn't put any programmable switching in here at all. Okay, so once the clock is brought in from the regular island style routing, it goes to every single one of these flip-flops. So that's kind of different, right? I didn't put in all this extra muxing. Is that a good idea or a bad idea? Why did I do that? So any thoughts on this? This is a good idea. Think of any reason why I drew the clock differently? Okay, so Camilo's saying a good idea, the fan out skew is decreased. Yeah, I do want low skew. So basically by keeping this clock simple, making sure it's got the same wire, basically everything, I'm going to reduce clock skew. How common is it that I need a different clock to every flip-flop? Now, how many clocks do you usually use in your designs? So I guess I'm giving you a hint. So inside this, basically, I should try to take, my CAD tools are going to try to take closely related logic and put them inside of these, there's one logic block. That closely related logic probably shares the same clock, right? So we do have different clocks in our designs. FPGA designs often can have tens of clocks, maybe even hundreds. But even in that case, that means the fan out of the average clock is 10,000. There may be some little ones where the fan out is 100, but there are other ones with fan out of 10,000, 100,000, even a million registers. So we usually have a clock that goes to a lot of different destinations, and you don't have that many. So you don't have that many unique clocks, and you don't have to put them in the same logic block, because generally those will be relatively loosely coupled parts of your circuit. So basically, the clocks need less flexibility than the general inputs to my basic logic elements. Every input to a LUT could be different. You're doing different logic functions, but it's rare for all your flip-flops are going to share clocks a lot more. So basically, this becomes a way to share resources that don't need as much flexibility. So they don't need the maximum flexibility. Okay, so essentially we can make some word wide. We think of the logic block as now our word, we can make them word wide signals. And so a good example is clocks. I might have lots of clocks in my design, but I probably don't need, if I have 20 registers in my logic block, I probably don't need 20 different clocks coming into the logic block. Other things that tend to make sense word-wise are clock enable. So clock enables don't have, you can have many more clock enables than you have clocks in a well-structured design. So you might have 20 clocks, and you could easily have thousands of clock enables. But even so, your clock enables are usually going to be entire banks of registers. So I think of some number that I've stored in a register, because it was actually in several 1-bit registers. So maybe I've got a 5-bit number. The data input to every one of those bits is different. You think back to your lab 1, what you were storing into every bit of a word would be different, but the clock is going to be common. And whether or not you enable that clock is also going to tend to be common. So a clock enable just basically says my clock. And a clock enable just says, keep your old value if the clock enable is low. And it's common that everybody in that whole data word. So in lab 1, you had 16-bit data words, and you notice that you had logic that would say, I either want to update this data word or I don't. But you didn't have logic that would say, I want to update bit 3 of this data word, or not, but maybe I want to update bit 4 at a different time. That's rare. So clock enable also tends to be word wide. So its fan out is less than a clock, but still significant. You don't need as much flexibility. Your reset signals, asynchronous clear, synchronous clear, they tend to have very wide fan out as well, because you usually reset, either your whole design or a large block of circuitry. So all of those, what are often called secondary signals, can basically go in with more restricted flexibility, just be broadcast to everybody inside the logic block. So we have programmable routing to allow us to decide, what clock, what asynchronous clear, what synchronous clear, etc. do we bring in from the programmable routing. But once we bring it in, we just broadcast it to everybody in the logic block, and it works pretty well because we just didn't need nearly as much flexibility. And this logic cluster gives us a good way to do that. Okay, so you wind up with, registers are good examples of this. So you have an asynchronous clear, you have a clock, you have a clock enable, you have a synchronous clear, and all of these signals tend to basically be word wide. But its data input, D, is basically different for every register. So this tends to be bit wide. And that's why the data input comes from this local routing that has additional flexibility. All these other secondary signals come from, will have less flexibility. And a logic cluster lets us do this. I also see a comment from Liam that the inputs from the cluster can be less than the sum of inputs for all BLEs, and that's true. So that's what the paper you read this week talked about. So that's essentially another manifestation of Rent's rule. So we're able to make a small hierarchical FPGA. We don't have to bring as many inputs into it, and that helps us make this more efficient. Let's see. The last positive is probably pretty subtle and not talked about much in the academic literature, but industrially, there's another advantage to this. So basically, FPGAs are not actually just logic blocks anymore. They're a whole bunch of different function blocks. So logic blocks, RAM blocks, DSP blocks, IO blocks, other stuff. Okay, and you have to lay all those things out, and they all have to line up nicely in a grid. So the programmable routing wires, the wires of this island style routing that I'm drawing here, kind of line up nicely as you go from logic blocks to maybe here I put in some RAM blocks. Okay, when I go from logic blocks to RAM blocks, the programmable routing has to keep going. And then maybe here I put in some DSP blocks. Okay, so we need to kind of match these layouts where all the routing wires, basically can go straight across these blocks. Okay, and that's a lot easier to do if basically these blocks are more similar in size. If the logic block, the RAM block, the DSP block, they don't have to be exactly the same size, but if they're more similar, it's basically easier to lay out this chip where the routing wires kind of go across them all. They don't get bent. You don't wind up with areas where you have wide channels and areas where you have narrow channels. Everything just kind of works out better. Okay, so the logic clusters, by grouping multiple BLEs together, the logic clusters are closer in size to other function blocks. And I just showed you some of those, right? So RAM, DSP, and there's lots more. And that makes it, I guess it makes it easier to lay them out, and it's easier to design the routing. So the design is not just the layout. This does simplify the layout, but the other thing is you're gonna see this in the next part of this lecture. But basically, if we have some blocks that have a lot of inputs and outputs, and we have other blocks that have very few, they have different demands on the routing. And that would make it very hard for us to choose what is the routing channel width and just pick one channel width and have it go through all the blocks evenly in the way I've shown here. So basically, if we have wildly different sizes of blocks, it is more difficult to design the programmable routing to satisfy them all, and it's more difficult to lay them out. By grouping together a bunch of these BLEs, because logic elements are pretty small. You know, a lookup table, the flip-flop's pretty small compared to a RAM block or an entire multiply accumulator unit. By grouping a bunch of them together with local routing, we make something that is larger and more similar in size to some of the other things we want to hook up to the programmable routing. So it makes our life easier. And that's it for all the positives I can think of. There is a negative to this, and the negative is basically even short wires. And these local wires inside here are pretty short. Okay, so when I'm talking about short wires, this local routing, here, let me get another type of highlighting. So this local routing here, you know, works well because the wires are pretty short and the muxes aren't too big. So that's what makes it fast. But as we keep scaling down process technology, wire resistance just keeps going up. So even short wires now have significant R and C, resistance and capacitance. And you know, that's actually what kind of really challenged hierarchical FPGAs. So when even the local wiring inside a logic block starts having significant resistance and capacitance, maybe that means that some faster routing architecture is possible. If we basically break up those local routing, break up that local routing into something more island style, something that's more based on a 2D distance grid. And it's not clear exactly what will happen there. In their latest chips, which we'll read papers on towards the end of the course, Intel actually is kind of making their local routing less regular because of increasing R and C. And Xilinx is actually making their logic clusters bigger and more regular because they say that they really need to, you know, have bigger clusters so that there's less pressure on let me see if I can highlight this again, on the general island style routing that goes in between them. So it's kind of interesting. The two biggest FPGA vendors are kind of going in opposite directions. They're both using this concept of logic clusters, but Intel is saying they're going to make or they are in their absolute latest chip, making this local routing more complicated to deal with R and C, and that's kind of making the abstraction of this is a nice simple hierarchical FPGA a little less true. And Xilinx is going the exact opposite way, saying they have to make this logic cluster bigger because the island style routing in between faces challenges from resistance and capacitive scaling. But anyway, we'll read a couple of papers on that towards the end of the course, and you can draw your own conclusions about you know, what all of that means for the future. With that, I'm going to take a break let's take a break till about for 7 minutes to 5:22, because I'm a little behind, so I should probably pick up the pace a little bit. I'll be on the line, so if you have any questions, just ask them, and we'll start again in 5:23. That gives you a 7-minute break. Okay, so let's start up again. Okay, so I'm gonna move on to a different topic, related topic, but a little different. Andrew, can you see this? All right, looks like it's all
I can see it
up now. Okay, so we're going to start looking at. We went through 3 kinds of FPGA architectures. We went through a few logic element architectures. We saw LUTs really dominate. Then went through different ways you can organize the interconnect, and island style nowadays mixed with some hierarchical routing for the logic blocks dominates. Now, if we want to go further than that into more detailed quantitative results, you have to put together a complicated CAD flow and area and delay estimation. You basically can't model most of this stuff analytically. So if you really want to know, is this particular idea better than that idea, you actually have to do what was in this week's reading and build an entire CAD flow run a bunch of benchmark circuits through it, estimate area and delay in a bunch of different chips and see what the trends are. And we will go through a bunch of papers that have done exactly that. But to gain insight of what is going on in those kind of evaluations, it's useful to do an analysis by hand. So you can see, well, how do you build that circuitry? How do you what are some of the trends in its area and delay? So we're going to estimate. So we're going to do that in the rest of this lecture. We're going to build a simple FPGA at the circuit level. So what would the schematics look like? Estimate the area, and then see, okay, with those simple estimates, how much area would go into the logic versus the routing. So we're going to do that for a fairly simple architecture. So a single 4-input lookup table per logic block. So not that cluster-based logic blocks. We're going to do a single LUT per logic block. All of our routing wires are going to be length 1. So they only go past one logic block before they end. And all of our routing switches are multiplexers. There are multiple ways you can build routing switches. Multiplexers are actually a pretty good choice. We're going to use it. Okay, so this is our basic architecture. So we've got W tracks for channel. We already talked about W. Our logic block is a single 4-LUT, so 4 inputs, 1 output. And we have muxes that allow us that basically form our input connection block. They allow us to choose what routing track, if any, connects to a certain input of this LUT. And then all of our routing switches to drive the routing wires are muxes. Okay, so we got a mux here that we can take a signal out of a logic block. It can be one of the inputs to that mux. So it's one thing we could choose to drive this routing wire. And the other things that can drive it are other routing wires near it. In this case, there are 3 other routing wires that can drive it. And what I've drawn in a box here is the layout tile. If we lay out this 4-LUT, the muxes that allow us to connect to its inputs, and the routing channel to its right and below it, repeating that tile over and over again would actually produce the entire FPGA. So we can model the FPGA of this, or the area of this FPGA, just by figuring out what circuitry do we have to build, and how much area will it take to make this basic tile. Okay, so one of the things we're gonna have to do is we're gonna have to work out how do we build all that stuff out of transistors. The other thing we're gonna need to do is I'm not actually gonna sit there and do layouts of everything. We're gonna estimate from transistor level schematics how much area is this gonna take on the chip. And that's, again, commonly done in FPGA architecture research, because to lay everything out would take a really long time. So we really just want to get a metric that correlates pretty well with final layout area. And the most widely used one in FPGA research is called the minimum width transistor area. So it's the smallest transistor to which we can connect, plus its spacing to its neighbors. All right, so the green here is diffusion. The gray are my contacts, and the red is my gate. Okay, there's every fabrication process, has minimum values for how narrow can we make this gate, how small, or basically what's the smallest width we can make for this diffusion, how big are the contacts, and so on. We actually want to be able to connect to our transistors, so we don't want to know just what's the smallest width we can make. We want to make the smallest transistor we can where we can still get contacts down, so we can still connect to it. And that basically, so a minimum width transistor is the smallest kind of generally useful transistor that I could make in a certain process. It's got the smallest width they can have where I can still actually get a contact down. Now I want to make many transistors, so I also need to consider what's my space to neighboring transistors. So a bunch of design rules that are going to define how far away does the next transistor have to be vertically, how far away does the next transistor have to be horizontally. Hopefully that all makes sense. Okay, so it's a good question for Camila. When you say process technology, which of these distances are we talking about? So the typical way that a process technology is defined is by the gate length. So this is L. So when I'm doing a minimum width transistor, I'm also using the smallest L. And most transistors will actually, in a certain process node, will use the smallest length they can because it makes them the fastest. Okay. Width, a transistor gets stronger, has higher drive strength as you increase width, but it has higher drive strength as you decrease L. So usually you make everything you can the smallest L, because it gives you higher drive strength and it saves area. So it's a nice win. This L is what normally defines the process technology. So in a 14 nanometer process, that's what would be 14 nanometers. Process technology has gotten complicated enough that there are lots of different numbers that you could use. This is the dominant one, but there's some marketing as well. So, that's why you wind up with one foundry will say they've got 14 nanometer, another will say they've got 16, another will say you got 12. It's hard now to compare process technologies just using the process number that is published. So for example, TSMC's 7 nanometers is generally believed to be around comparable to Intel's 10, just based on the way they count. But the basic answer is that it corresponds to the smallest gate length. And then on top of that, you layer sort of some marketing claims, and everybody would like to have a small number because it looks good. Does that make sense? Okay, so that's this unit minimum width transistor area. Now, we're not going to make every transistor the minimum width because, well, it would be very area efficient. That's the smallest transistor we can make and still connect to it. But we're going to need some transistors to be stronger. If they're driving a large capacitance, they're going to be really slow if we make them minimum width because they don't have much drive strength. So some transistors are going to naturally have to be bigger, and that costs area. So if I make if I have a transistor and I need its drive strength to be twice the minimum, and remember that the transistor drive strength is proportional to width over length. Generally, I've made this length as small as I can. So if I want higher drive strength, what I've got to do is make the width bigger. So if I need more drive strength, I can make, say, I can double the width of the transistor. And it doesn't actually double my area because I don't have to increase my spacing to other transistors. So this part, basically this green increased in height, but the spacing to the next transistor didn't increase. So it didn't double my area, but it did increase it. The other thing I can do is I can basically I can put multiple transistors in parallel. And that's another way I could get more drive strength. So here I could connect, let's say I want to make an inverter that's twice as strong. And let's say this is the pull-up of that inverter. So I connect this to VDD, I connect this to VDD, and I connect this to the inverter output. And what I've got now basically is 2 transistors in parallel. Each of them has the minimum width. Together, they have twice as much drive strength. This also added area, but it didn't double my area because if I had made just one transistor, it would have ended around here. Instead, I've added this extra stuff onto it. And I don't have to increase my spacing to the next transistor either. So they both increase the area, but not double. A very simple estimate of the area would be you take the transistor drive strength and you call that X. Okay, so it's 1 if you want the smallest drive, you're okay with the smallest drive strength that you could get. It's 2 if you need double that and so on. And your area in this minimum size transistor unit is 0.5 plus 0.5x. So it's simple and it actually works reasonably well. So if you want the smallest drive strength, it means you get an area of 1. If you want a drive strength that is twice as big, you get an area of 1.5. If you need a drive strength that's 4 times as big, you get an area of 2.5, and so on. The paper that you read a couple of weeks ago uses a more complex but more accurate formula that basically reflects the fact that sometimes it's best to combine these two things. So instead of deciding I will widen my diffusion or I will go parallel, sometimes for big transistors it's best to do a mix of those two things. And this paper considers that. And then the paper down here is one that actually did a whole bunch of layouts to say how accurate is this, and it came up with basically it concluded it gets the right basic trend, but none of these are perfect, so it came up with some more correction factors. But for doing this by hand, I want to keep it all pretty simple, so we're going to use the simplest of all these formulas, which is this one. So that's one I'm going to be using in the next slides. And it's, as I said, it's reasonable, but if you basically go off and do research on this, then probably you want to use the more accurate formula that's in here. Okay, so any questions on that, or does that all make sense? I'm going to interpret silence as makes sense. maybe a dangerous assumption, but I think that default will move me forward faster. So jump in if you have any questions so far. Okay, so we want to basically start looking at how big the logic and the routing is in our simple FPGA. 1 4-input lookup table, all length 1 routing wires. So to do that, we need to actually go off and make some transistor level schematics. Okay, so let's make some transistor level designs for basic components. And the first basic component that we're going to need is we're going to need to do the lookup table. All right, and we've already looked at what a lookup table is. It's SRAM cells feeding a multiplexer. Okay, so I've got SRAM cells. I'm just going to do a 2-input lookup table. Well, draw a 2-input lookup table because it's already lots of transistors to draw. These are generally done with pass gates. Okay, so pass gate logic is a tricky circuit style, but it's very efficient for things like multiplexers and lookup tables. So it's what FPGAs use. And it's part of why FPGAs are designed, kind of at the transistor level, because they're using somewhat dangerous, tricky circuit styles, but they are more efficient. Okay, so let's see how well I can draw this. Okay, so my inputs to a 2-input lookup table, I'm going to have 2 inputs. So let me draw all the, let's see, think of what the best way to draw this is. I haven't drawn this in OneNote before. Let me just draw all the multiplexer transistors first. Okay, so they're all my pass gate transistors, and this is my truth table. These are SRAM cells over here. Okay, so let's take my first input. If my first input is high, and maybe I'll do this in a different color. That might make it easier to see. Okay, so let's say this is my input is high, input 0 is high, I'm going to activate these 2 transistors. Okay. If my input is low, okay, so I need to invert the input as well. And let's see. My input is low, I want to activate these 2 transistors. Okay, so that's my first stage of muxing. That's basically a 2-to-1 mux. Okay, I have another input, call that input 1. And input 1 comes in, I'm also going to invert it. So I have the true and the complement available. Okay, so if it's true, I'm going to activate that transistor. And if it's false, I'm going to activate this transistor. Okay, so hopefully everybody can see that that is a 2-to-1 mux. Okay, this has poor drive strength. I've gone through from an SRAM cell. Let's say my input is 1, 1. Then if my input was 1, 1, then my signal path is going to go like this out to here. And I've gone through 2 pass transistors, which means that the output drive strength is not going to be very good. It's like I doubled the resistance of my pass transistor by doing that. And I probably don't want to make these, and I got a potentially big routing wire after this. So I put an inverter here so that I can basically increase my drive strength. Now any downstream capacitance gets discharged to ground or VDD by this inverter rather than having to drain all the way back through these pass gates. Okay, so that's my 2-to-1 mux. Is there anything here that worries you? Am I missing anything? I guess I am missing something. What am I missing? If you read the paper from a week ago carefully, you'll know that there's something bad about this, what I've drawn. I need to put something else in here. the buffer is missing. So I've got a buffer here. Well, I've got an inverter. I haven't put the second, I guess, yeah, I haven't drawn this, but there is, if there's a big routing capacitance downstream, I would put another stronger inverter after this. To keep the kind of math simple, I'm not going to bother putting this in, or I'll put it in later when I talk about the routing drivers. But for now, I won't. Yeah, the other thing I'm missing is level restoration. So remember, a pass gate does not pass it passes a logic 0 fine, but this signal will range from 0 to VDD minus V threshold. So we don't get a clean 1 out of it. And that is going to make this inverter really leak, because the inverter is built out of a pull up and a pull down. When we pass a VDD minus VT onto its input, the pull down is strongly on, the pull up is weakly on, and this thing leaks like crazy. So we get a degraded waveform and we get lots of static power. So we don't want to do that. So the way I fix it, I'm going to erase a couple of these lines. So the way I fix it is with the level restorer. Okay, so a level restorer is just a weak transistor. So we intentionally want to make this one not very strong. And it basically can pull up a signal. So when this goes to, when we put a logic 1 here, this goes to VDD minus VT at this node. That's enough that this inverter pulls this node low to close to 0. That turns this signal on, which will basically start dumping charge onto this node and pull it the rest of the way up to VDD. And once we pull it the rest of the way up to VDD, this inverter will stop leaking. So we're all happy. Mod has got a good question. Shouldn't this be VDD minus VT in the output? And the answer is no. You might think that, but basically no matter how many pass transistors you go through in series, you only lose 1 threshold voltage. And after the class is over, if you want, I can show you why. When you work through all of the voltages, basically what makes a pass transistor drop that threshold voltage is it shuts off once its source is at VDD minus VT. And if you walk through a series of pass transistors in series, you'll see that basically that only happens once. You won't lose 2 VT by going through 2 in series. Does that make sense? Okay, so yeah, so we built this schematic, and now I want to count how many transistors are in it. Okay, so number of transistors. So first I've got, let's do it for this as 2 input LUT. So this is a 2 LUT. Okay, so I've got SRAM cells. So I've got 4 SRAM cells. How many transistors does it take to make an SRAM cell? Anybody know? Yeah, 6. So an SRAM cell, basic SRAM cell is basically cross-coupled inverters. And then you put a couple of access transistors on it so that you can write in new values. Okay, so that's like D and D bar, and this is your control line. And that's a relatively simple, relatively safe SRAM cell. In theory, you might be able to do this with 5, but it's super risky. So number of transistors for an SRAM cell, we're going to use 6. So we got 6 transistors per SRAM. There are 4 SRAM cells in this device, this lookup table. So that's my SRAM. All right, then I have, let's see, 1, 2, 3, 4 pass transistors in the first stage, 2 in the second stage. So I have 6 pass transistors. So we'll call that P trans. Then I've got 1, 2, 3 inverters. Every inverter takes 2 transistors, so 6 transistors in the inverters, and plus 1 more in this keeper transistor. Okay, so that's equal to 37. All right, but I don't want this just for a 2 input lookup table. I want to get the general form. So the general form is 6 transistors per SRAM cell. We already saw for a K input lookup table, there are 2 to the K SRAM cells. Number of pass transistors. Well, basically it's 2 to the K for a K input lookup table in the first level. Let's see, let me highlight this. So in the first level, I've got 2 to the K. In the second level, I've got 2 to the K minus 1 and so on. So if I add all that up, the sum of that series is 2 to the K plus 1 minus 2. Okay, and the reason it's minus 2 instead of the usual formula of minus 1 is we don't, when we're down to one pass transistor that would always be on, we just remove it, right? So we don't put the last part of the geometric series in. Okay, and then we have the inverters. The number of inverters we need for this is equal to the number of inputs plus the number of outputs, which is 1. So it's just K plus 1 inverters. And then we have one more transistor for that weak keeper. So that's 2K plus 3 more. All right. So just like we saw before, this is exponential in K, which means we can't make really big lookup tables. It's going to take a lot of area. This is just counting transistors. So, and I said we really shouldn't just count transistors. We should try to estimate their area. So some of these transistors are going to be bigger than others. The transistors in the SRAM are generally very small. Okay, so the SRAM does not have to be fast. We're going to write it when we configure the device, and then we're just constantly reading it. It never changes. So we can make all these transistors quite small. And the layout of a SRAM is really optimized because you repeat it so many times. This is one where actually commonly companies will basically violate design rules and check that it's okay to get a more dense layout. So for the SRAM, we can assume they're all minimum size transistors, so six area units. Even if some of them aren't quite minimum, the layout is so dense we can assume 6. The pass transistors here actually have to drive. Pass transistors are pretty speed critical. We have multiple pass transistors in series. So here we have 2 in series. And they're loaded by this downstream inverter. So we're going to make the pass transistors a bit bigger. It's probably not obvious that that's a good idea unless you go off and do some spice runs. So take my word for it. The pass transistors turn out to be the speed critical part of this. So we're going to make those bigger. So let's say K equals 4. So we're going to do a 4 input lookup table. And we're going to choose the transistor size. Actually, let's not call it size. Let's call it drive. Let's call the drive strength of the pass transistors is equal to 5 units. So 5 times minimum. If we plug those numbers in, then the area we would get, remember there are 5 times, if we make a pass transistor have 5 times the minimum drive strength, then it's going to, by our simple formula for area, that means the area of a single pass transistor would be 0.5 plus 0.5 times 5, which would be 2.5. Okay. If we plug that area in, all these transistor sizes into our simple area equation, we would get area of this whole thing is equal to 217 minimum width transistor areas. Make sense, everybody? So we've got our first order estimate of area, and that's an important area. So we wanted to estimate the area of our simple logic block and routing. Well, the logic block was basically a 4 input lookup table. We just estimated its area. Okay, but that's not everything. So we've got the LUT. Now we need to look at how it connects to the routing. And remember, it had a mux that allowed it to select from one of several routing wires. So that's its input connection block or an input routing port. So what's the area of this, this input from the programmable routing? And we're going to need 4 of them, but we just need to know what's the area of one of these. Okay, so that's a multiplexer. It's a multiplexer controlled by Sram cells. right? So I haven't drawn them here, but there are SRAM cells controlling this. Okay, so how are we going to build that? Well, we saw in our lookup table, we needed to build a multiplexer there, and we built it out of Pascades. So that probably is a good idea here too. So we're going to build a routing multiplexer out of Pascades. What the thing that's going to allow us to select, basically out here, we have routing wires. The thing that's going to allow us to select which routing wire goes into this lookup table. Okay, so there's different ways that we could build this routing mux. So the simplest one is I just build a bunch of pass gates. Okay, so this is a routing wire 0. And if I want to select that, I program this SRAM cell here to be on, and I get a value coming out, and it goes through an inverter. And I know this is a pass gate, so it's going to degrade my logic. So I'm going to put in a level restorer, and yeah, it's my output of my routing mux. This was my first input. I don't want to have just one input. I want to have a whole bunch. So I repeat this structure over and over again. So that's in 1, ... And I'm going to do a relatively big routing mux with 32 inputs. Okay. So what I've drawn here is called a one-level mux. So it's a pass gate mux, and I don't have any pass gates in series. So I only have to go through one pass gate to get from input to output, plus a buffer. Okay, so let's look at this way of building a mux. So number of transistors is equal to number of transistors that I need for an SRAM cell, which is 6. Okay, so for every input, I need an SRAM cell and I need a pass gate. Okay, so 6 transistors in the SRAM cell, 1 transistor in the pass gate. I need that for every single input. And then at the end, here, I've got this structure. And that structure is independent of the number of inputs. It's just another 3 transistors, 2 in the inverter and 1 pull-up. Okay, once again, this is going to be a fair amount of capacitance. Got a bunch of metal here, all these pass gates hooked together, input to this buffer, etc. So I'm going to make my pass gates bigger than minimum again. So this one is the pass gate, and I want to make it bigger. Okay, so when I go for area, I'm going to make all my transistors the minimum size. So I just have 6 SRAM cell transistors that are all small, but then I add in the area of this pass gate, which is 0.5 plus my drive strength of the pass transistor divided by 2, because that's my formula for area. All of that is multiplied by the number of inputs, and then I add in 3. It's actually kind of messy. Let me move this over a little. Okay, so I plugged some numbers in for this. If I say the number of inputs to my routing mux is 32, and I basically make the T drive of the pass transistor equal to 5 times minimum, then it implies my area is equal to 291 of these minimum width transistor areas. Okay, so which seems pretty big. Okay, so let's circle that number. That's the area of one of these muxes. Okay, that's just one of these. I actually need 4 of them. And the area of my whole LUT, which is up here, was only 217. So basically the area of that routing mux, that routing port, is bigger than the whole LUT, and I'm going to need 4 of them. So that's showing routing is pretty important. But that's not the only way we can build a mux. Okay, so I built this mux essentially fully decoded. Every pass transistor is controlled by one SRAM cell. So what are other ways I could build this? So any idea? Is there another, like, how do we build it for the LUT? So we didn't build it quite this way for the LUT. So could we do it a different way and maybe save some area? Bunch of logic gate connect. Yeah, okay, so I could give up on pass transistors completely, and I could just build this as like and or gates, but it turns out that's actually a lot bigger still. So pass transistor logic will save us area over switching back to basic logic gates. If you want an FPGA that's simpler to design, sometimes it's done for embedded FPGAs where you're actually going to integrate it into a larger SoC. So it's not Intel or Xilinx FPGAs, but you bought like from Flex Logic, for example, you might buy an FPGA that can be integrated into a larger SoC. And there's some advantage there to using simpler circuit design styles. So they might do it with logic gates. But for the big FPGAs that are kind of custom manufactured, pass transistors will save you a lot of area. So any other ideas? What can I do topologically to this? Tune the size of each level for multi-level multiplexer to give the best area. Yeah, so that's a very good idea. So yeah, this is a one-level mux. We can kind of do muxing in stages, multiple levels. And so that's actually the general answer is basically, well, we could think of how many levels do we want to do the muxing in. So let me look at the other extreme. We looked at one level. Now let's look at K levels. So K level mux. So if I'm doing 32 inputs, then I could do this in 5 levels of muxing if I wanted. That's the most levels that kind of makes sense. So let's draw what that is. So basically I can have an input 0 and I can mux that down. It basically looks a lot like my lookup table. So I have an input 0, input 1, input 2, input 3. I'm not going to draw all 32 inputs for the example I'm doing. And I basically have an SRAM cell here that will turn on that cell and that cell. And let me change my color. And I can come off of the, actually I shouldn't have drawn this way. Let me erase that. Okay, so let's say I can come off here, off the true side of the SRAM and control 2 of these transistors. And I can come off of the false side of the SRAM. So it's a pair of cross-coupled inverters. So I'm assuming I can just tap into either side of the SRAM. So that false side of the SRAM, I can control the other 2 pass transistors with. Okay, and I need to connect all this together. So this is basically a tree structure. So that's my first level of muxing. Now I need to do my next level of muxing. And I should say that these wires continue on down here too. Okay, so the second level of muxing, I've got another SRAM cell. True side controls that. And the false side goes down here, controls that. Okay, and so on. So then I have my next level of muxing, which I'm only showing one little bit of. And this continues on for a while, for 5 stages. If I'm going to do a 32-to-1 mux, which is what I'm doing. And eventually I get my standard output circuit of an inverter and a weak pull-up. And it looks like that. Okay, so if I add up the number of transistors in this, it's basically log base 2 of the inputs. That's how many SRAM cells I need. I only have one SRAM cell controlling each stage. So log base 2 number of inputs times the number of transistors. Okay, so that's my SRAM. Plus 2 times the inputs, which is my 2 times the inputs minus 2. That's basically what I get from the pass transistors. Plus 3 at the output. Okay, so that's the inverter and the keeper. If I plug in the same numbers I had before, so say inputs equals 32, T drive, I'm going to make my pass transistors extra strong, so they're 5 times the minimum drive strength. I plug in my area model, plug in number of transistors of each type. I get an area of 219, again, of these minimum width transistor areas. So that's actually quite a bit better. Okay, so the area was 291 for one of these 32-to-1 muxes. It's now dropped to 219. So it's a lot better, but our lookup table way back up here, let's put a LUT on that. Area LUT was 217. So it's now down to about the same size as the LUT, but it's still pretty big. What about speed? What do you think? Is this changed from a 1-level mux to a, for 32-to-1 inputs, it's 32 inputs, it was a 5-level mux? Is it going to be faster, slower, no impact on speed? What do you think? It's one of those questions where it's 50-50. So just take a shot. So what do you think? Faster or slower than a 1-level mux? Yeah, so it is slower. It basically, because you've got more pass transistors in sequence, a reasonable model of this is you replace the transistors in your mind or even in equations by resistances, and then the delay is the capacitance that has to be discharged by every resistance. You just add all that up. So basically, we've got 5 times as much resistance to this final capacitance here. It won't actually be 5 times slower, but it will be slower. Okay, so speed is slower. Okay, so we've got a trade-off here. Okay, but Kimmy already gave a good idea of, well, why do only the extremes? We've done 1 level, we've done so kind of fully decoded mux or fully decoded SRAM. We just did K level, which is fully encoded, like the most levels we could possibly use. We could look at ones in between. So we could do a 2-level mux, for example. And this is the mux that the paper assigned a little over a week ago looked at. Okay, so what we do here is we basically are just going to cascade 2 1-level muxes. But then Fpgas let us do an optimization, which is basically we can share the SRAM across all 1-level muxes. Okay, so let me show you what I mean by that. Okay, so if we have a 32-to-1 mux, I'm not going to draw all the individual pass transistors, but you can see them in the notes if you like. We can basically do that as an 8-to-1 mux. Okay, so let's say that's an 8-to-1 mux, and we can repeat that 4 times. Okay, another 8-to-1 mux, another 8-to-1 mux, another 8-to-1 mux. So we've got, and each of these are built with 8 pass transistors and 8 SRAM cells. Okay, so we're going to need 8 SRAM cells. Let's see, so 8 SRAM are going to control these. So that's what we'd have inside here, controlling the pass transistors. And then I take the outputs of each of these and send them off to another pass gate. And each of these gets its own SRAM cell. So this is basically my second level mux. And then I short all these together. And then this goes out to my standard output circuit. So inverter and a keeper transistor or level restorer, whatever you'd like to call it. Okay, so that's my output. And I have 32 inputs. Okay, so the key thing to saving area with this is to recognize that if the path I want to activate, let's see, try to get this, I get a highlighter here. Say the path I want to activate is this one. Okay, so I want to select the first input of this mux, and then I want to program a 1 in here so that it goes all the way through into the output. If that's the path I want to get, I do not care about what happens in any of these other 3 muxes. Okay, so these 3, when the signal I want is the blue one, are don't cares. And that's always true. There are always 3 of these 4 muxes are always don't care, because I want to get the signal from one of the muxes. Like I want to get one of these 32 inputs. That means whichever mux it feeds, I care about how it's programmed, which signal makes it from input to output, but I don't care about the programming of the other 3 muxes. So this one, and this one, because their signals aren't going to make it through the second stage of pass gates anyway, right? So they won't make it through here, so I don't really care. So what I can do then is I can basically share these SRAM cells. So these 8 SRAMs, I've only drawn 4, but there would be 8 of them here, basically go to all of these muxes. So that trick, realizing that I don't care what happens in muxes that aren't going to make it through the second level, means I can share these SRAM cells. And so is that clear to everybody? Is that clear why I could do that? So I think I'm going to take that as yes. I probably should have asked that question the other way around. Okay, so that's the basic way that a 2-level mux works. And now let's add up the number of transistors. So number of transistors, and let me see if I can get a thicker pen. I'm probably being too thin here. Okay, number of transistors is equal to 8. There are 8 SRAM cells in the first level. There are 4 SRAM cells in the second. So there's 12 total SRAM cells times 6. So 6 transistors per SRAM. So that's my SRAM transistors. Plus the number of pass transistors in the first level is just 8 times 4, or 32. And the number of pass transistors in the second level is just 4. So these are my pass transistors. And then my output circuit is again 3. Okay, so if I plug in inputs equals 32, and the transistor drive for the pass transistors is 5 times min, then I get area equals 183 minimum width transistor areas. So this is good. So basically this actually turned out to be smaller than either the 1 level or the kind of maximally encoded one. It's definitely faster than K level. The 5-level mux that we did would be slower than this. And it's usually not quite as fast as the 1 level, but it's close. Even though it has 2 pass transistors in series, when you analyze the details of it, the wiring is shorter. So that actually makes it faster than you might think. And if you have a lot of inputs, this actually can be as fast as a 1 level. If you have a small number of inputs, then it's usually slower than 1 level. But it's a pretty good choice. And it's actually the dominant choice in most FPGAs. So FPGAs actually do exactly what Kimia mentioned, of explore all the options of how many levels you're going to do. Usually the best choice for small muxes, 1 level is usually the best, but small means, maybe 4 to 1 or so. And once you get beyond that, 2 levels, usually the best, but not always, but it's the most dominant one. Okay, but we step back for a minute. But this is kind of like not a great story in terms of routing area. The LUT is what's doing our logic, kind of our computation. These routing muxes are just getting the signals there. So each one of these routing ports or input ports is close to a 4 LUTs area. And we need 4 of them. Okay, so that's a lot of area. So it means you can't neglect routing area. So there are some FPGA studies that have said, well, we're just going to count how many logic elements we used, and we'll come up with a new logic element, and maybe we'll multiply by the area per logic element. But we're not going to worry about the routing because it's kind of hard to estimate. And you can't do that because the routing is commonly bigger than the actual logic elements. So you can't ignore it. You have to have some model of how big the routing is. Okay, so we now need to, we've got our estimate of the LUT area. We've got our estimate of the inputs to the LUT, these input ports or connection boxes. But we don't have, actually I have to go back here. We don't yet have a model for this. Okay, so we basically figured out the area of that. We figured out the area of these muxes that allow us to connect the routing tracks. We have not worked out the area of this. All of these muxes that are inside the routing fabric and driving the routing wires. So we need to go back and do that. Whoops. Let's just try not to do this. Okay. Okay, so now we need to estimate the general routing area. And by that, I mean all of the muxes that are driving the routing wires themselves. Okay, so how are we going to do this? Okay, so the best way to do it would be use a full CAD flow. Okay, so that's definitely the best. It's what the paper that you read this week does. But that's not going to give us much intuition. And it's important that you have intuition, because otherwise if if you get a certain answer from a CAD tool and it's completely wrong, or the CAD tool is doing a bad job, if you have no intuition about what's going on, you have no ability to sanity check that. So we want that intuition. Okay, so I'm going to build a simple model below to gain intuition. Okay, so one of the things that we're going to need to know is how wide do we have to make these channels? So let me go back here again. We've got W tracks per channel. What should W be? I don't know, right? It should be enough that most circuits route, but not so much that I'm just wasting lots of area. So that's a pretty vague spec. So I need to figure out what should W be. Something that can help me is this equation. So the average channel width that I'm going to need is lambda times R bar over 2. Okay, so what are these things? Lambda is the number of used inputs per block on average. Okay, so if I have a 4 LUT, I know that lambda is no more than 4 because I only have 4 inputs. So for sure, the average block can't use more than 4 inputs. In fact, the CAD tools usually can't use all the functionality of a LUT all the time for all sorts of reasons. Maybe you just have not that much logic between 2 registers and so on. For a 4 LUT, lambda is clearly going to be no more than 4, but it's actually about 3.5. which isn't that far off 4. But it's basically the CAD tools can't fully utilize the 4 LUT all the time. Sometimes they only use 3 of its inputs, maybe 2 once in a while, on average 3.5. Okay, so that's lambda. What's R bar? R bar is the average distance that we have to travel to go from the output of a block to the input of the block it's trying to drive. Okay, so from output to input. And divided by 2 comes from the fact that there are 2 dimensions. Okay, so let me show you what I mean by that. Okay, so R bar, here are 4 blocks. If this block wants to connect to this block, so I've got some signal A that needs to be connected here. Let's just draw that as, this is like net A. So net A needs to connect these 2 blocks. And they're 4 units apart. If every single connection in my design looked like that, then R bar would be 4. If some of my connections wanted to connect blocks three away, half of them wanted to connect blocks that are 3 units apart, and half wanted to connect blocks 5 units apart, R bar is still 4. Okay, so the average distance that we want to go from the output of some block to the input of where it's trying to go to. Okay, so there'll be a whole range of that in an actual implemented design, but the average matters a lot. So a design that's got good locality, R bar tends to be small. You go to things that are not very far away from you. A design that has bad locality, R bar is higher. This is a pretty hard one to estimate without more experience, but a good estimate of R bar is about 4. So across a whole bunch of different FPGA architectures that I've worked on over many years, it turns out that assuming R bar is 4 is actually a remarkably good estimate. Like it's not that accurate, but it's surprising it doesn't vary more than it does. So it means most connections are to relatively close by blocks. Okay, so what's the intuition of this? Like why does this happen? Basically, if we have more used inputs, we need more wires per channel. And that means we're going to need more general routing area. Essentially what happens, let's say I've got a 4 LUT here. Okay, so this 4 LUT has, let's keep it simple. Let's say that it has 4 inputs that need to come into it. So lambda equals 4. And let's say every one of those signals comes from 4 blocks away. So then as I draw these out, I'm going to have 4 wires that are overlapping in the channel. If that makes sense. And actually, this is probably not the best way to draw it. Let me draw this in a different way, because this is not going to look that regular. Whoops. Okay, I'm going to go down here and try again. I think I want to draw this in a slightly different way that'll be more realistic. So let's say I'm looking at this block and I'm seeing what happens for its inputs. This block drives its output to a block that is 4 units away. So it goes there. And then draw another color. This block drives out and it drives to something that is 4 units away as well. Okay. And then this block drives out also to a block that is 4 units away, and so on. Okay, this one also drives away to something that's 4 units away. And now this block, so far I've just done its input. Now I do its output. Its output also goes 4 units away, but it doesn't overlap the first route. Okay, basically the first route is ended, so I can basically reuse that track, that part of the channel now for this new one. So in the steady state, I'm just drawing here the case where lambda equals 1. I'm just drawing one input to each block. So lambda equals 1. But R bar equals 4. And I'm doing it just in one dimension. So you can see in the steady state, we actually have 4 wires overlapping right there. And it's also 4 wires overlapping here. And if I continue this pattern, it's just going to be 4 wires forever. So if the average connection has to go 4 blocks, then if I only had 1 input to every block, I would only need 4 wires per channel. Now, if I actually have more inputs per block, then I'd have to do this for every single input. So if lambda equals 3.5, I would have to repeat this pattern 3.5 times. So basically repeat down this way. And my channel width would go up. So does this make sense? Hopefully the by 2 also now makes sense. If my average distance, I've done a one-dimensional FPGA. So my average distance, all my connections are only going horizontally. Real FPGAs are 2-dimensional. So if half of my wiring is vertical and half of my wiring is horizontal, then basically I only need a vertical channel to support half the routing and a horizontal to support the other half of this distance. So I get to divide by 2. So that's where we get this equation. The average channel width is lambda R bar over 2. So does this make sense? This has sometimes been called the Ohm's law of FPGA architecture. So if you don't understand this, let me know. This is basically like how does locality, R bar, and the number of inputs you need to get to every block interact with the channel width. So this is an important kind of basic trade-off rule that you want to understand. I'm going to take silence as that you get it, which again is maybe dangerous, but we're going to just keep going with that. Okay, so I've now got this, I can calculate W average. All right, so remember it's lambda R bar over 2. I said lambda is equal to 3.5. R bar, I told you, is typically about 4 divided by 2. So that's 7. Okay, so 7 wires per channel. But we can't use all the wires in a channel. At least not everywhere. Not in the typical case. You might be able to do it once in a while in one spot in the chip, but you're not going to be able to do that very often. You kind of got really lucky. So this W, it's the average number of wires per channel. It's not the peak. And to fail to route, all you need to do is need more wires per channel in one spot than you have, and your router fails. Okay, so we need to actually design for the peak, not for the average. Okay, so there's a few reasons. So we need to architect for the peak, and basically our bar is like an average. The distance that connections go actually varies. So there'll be some parts where we have somewhat longer connections and they're going to need somewhat wider channels. The other thing that's going to happen is the switch pattern in an FPGA is very sparse. Okay, so that means that you're limited in which wires you can connect to others and which wires can connect to the outputs of blocks and to the inputs and so on. So it means some wires are going to be blocked. Are going to be blocked by essentially the way you have to program the switches to use other wires. Okay, they're going to be blocked by other signals. You could put in a switch pattern that's much less sparse, put way more switches in, and then you'd be able to get closer. You wouldn't need quite as wide a channel, but it turns out adding too many extra switches is more expensive than just widening the channel. So FPGAs use quite sparse switch patterns because it's more efficient. Okay, so for these 2 effects, you have to add quite a bit, about 50% to 100% extra W. And some of this is how conservative you want to be too. Do you want some circuits to have trouble, or do you want to make that very rare because you don't like that? But if I now put in this W peak is equal to W average times this 1 plus guard band, that is equal to, we already figured out that our W average was 7. Let's just pick the middle of this range. So 70%, which is the geometric average middle. Then we get 12 wires per channel, which is a pretty reasonable number for a simple logic block like this. Like for a 4-let, it's a pretty simple logic block. Lambda's small. You can actually get by with pretty narrow channels. If you look at commercial FPGAs, their channel width is usually 200, 300, kind of 400, those kind of numbers. But their logic blocks are those big cluster-based logic blocks. Because we've chosen a much smaller logic block, we can get by with a much smaller channel. Okay, so we figured out an estimate of channel width. That's what we're going to use. So the next thing we want to do is we're going to assume, we're almost done with this, but we're going to assume a very simple routing architecture. Okay, so all wires are length 1. So they only go past one logic blocks and then they end, and they're all based on multiplexers. Okay, and my pattern of switches is going to be this. I have a lookup table. It's got an output. Draw a few lookup tables. Okay. So all length 1 wires, they're all short. And I'm going to basically, if I look at this routing wire here, I'm going to have a mux driving some kind of buffer or an inverter. And the switches that can go into it, it's important that I could have a signal that comes down from above. So I'll have 1 wire from above that can go into it. I'll have 1 wire from below that can go into it. I'll have 1 wire from the left that can go into it. And I'll have 1 logic block output that can go into it. So I just have 1 of every kind of wire. I want to be able to go have connections continue, whether they're coming from above, below, to my left, or start from a logic block. It's not obvious that this is enough flexibility, but if I don't have at least this much, it's probably going to be very hard to route. And we'll look at like some analyses of switch patterns later. But this is a fairly constrained, but not crazy switch pattern. So with this one, I need a 4-to-1 mux. Okay, because if I repeat this kind of pattern for every one of these routing wires, every one of these routing wires is going to get a mux, and each of those muxes is going to have 4 wires that feed into it. Does that make sense? Okay, let me put in this. This is my LUT. Okay, so let's work out this area. Oh, okay. What is the, okay, I actually missed a couple questions. Sorry. So what is the factor added by 1? Is that basically a question about this? Where did I go from 1? Why am I taking 1 plus? Okay, so this 7 is the W average that I computed earlier. Yeah, and this this 1 plus 0.7. So that's just the guard band. I basically said typically you need 50 to 100%, so I picked 70%. Okay, and that gets me from kind of average to a reasonable estimate of peak, sort of peak usable channel width. Okay, the second question is a good question from Gil of, do you need the same channel width everywhere, or can you vary it? In theory, you can vary it, and there have been some studies saying that that is actually useful. It's really hard to lay out though. So almost all FPGAs, not all, but almost all, choose to keep the channel width the same everywhere, because it's much easier to lay out. And then if you have some kind of hard to route and some easy to route parts of the design, what you do is the CAD tools try to spread out the hard to route parts or interleave them with the easy to route parts. They can't do that perfectly, but it's just such a pain to lay out different channel widths that normally you just make it all the same. Okay, but good questions. So I have to watch the chat carefully. Okay, so that's our simple architecture. And now we want to compute the area of these routing muxes. So the area of the routing muxes is equal to, okay, we need our SRAM cells. So we're building a 4-to-1 mux. So we need 4 SRAM cells, each takes 6 transistors. So 6 times 4 for the SRAM cells. We need 4 pass transistors. For really small mux like this, we're just going to make it out of a 1-level mux. So 4 pass transistors, we're going to make them 5 times the minimum drive strength. So we put that through our area equation. It's 5 plus, oops, I can actually erase, 5 plus 2.5. Okay, so these are my 4 pass transistors to make my 4-to-1 mux. And we're making them relatively strong pass transistors, 5 times minimum drive, pass trans. And standard at the end, we have an inverter and our level restorer, so 3 transistors for that. Okay, and if I add all that up, I get 39 of these minimum width transistor areas. It's the smallest transistors I can make. Okay, that was for one of those routing drivers, the mux and the routing driver. I've got more than that though. So again, my basic unit that I'm repeating is a logic block plus 1 piece of a vertical channel, 1 piece of a horizontal channel. So I'm going to need 12 of these routing drivers for the vertical wires and 12 for the horizontal. And that's my replicated unit. Okay, so I need W routing drivers times 2 different channels times the area I just computed. Okay, so I plug in the numbers for that. That's 12 times 2 times 39, which is equal to 936 of these minimum width transistor areas, which is pretty big. And this 2 came from, horizontal and vertical. Okay, so this is basically the area of the general routing. So this is another important number. Okay, so I can now add up what is the area of the whole thing. The area of this repeated tile is the area of the LUT, plus we have 4 inputs. We need the 4 times the area of an input routing port, which is just a mux, but a pretty big one. And then we need the area of these routing, what do we call that? Area of like the routing mux. Okay, routing mux plus driver. All of this stuff, these are just 2 different kinds of routing, right? This part is the interface into the logic block. This part is the interface out of the logic block mixed in with the connections between wires. So yeah, 2 of these terms are actually routing. Okay, if I add all that up, the LUT was 217 of these small transistors. Best implementation for the input ports, muxes was 183 of these minimum width transistor areas. And we just worked out that the general routing was 936. So the area of this is 1,885 of these minimum width transistor areas. And so if we actually compute what fraction of this is routing, because the only part that is actually doing logic is this part, we get that this is 88% routing area, which is big, okay? So don't neglect it. There are some papers, as I said, some old, but some recent, where they just neglect routing area because it's harder to figure out. But it's not a second order effect, it's a first order effect. And one of the things we'll find as we go through the course is basically this 88% is big. We will find better architectures that reduce it. So better arcs cut routing area, below this, but it's still at least 50%. Okay, so usually it's well above 50%, And I've never seen anything credible, like any credible architecture where it went below 50%. So it's a major effect. You can't neglect it. And I think that is all I'm going to talk about today. At the end of the slides that I posted is just some discussion on the Microsoft Brainwave paper that you read a week and a bit ago. Maybe I'll go over that at the very start of next class, but you can read that. It just covers some highlights from the Brainwave paper, along with a few related pieces of work from papers that were published after it. And if there are any questions, I'll stay on the line, but otherwise we're done.
I have one question. So these routing architectures, are they all two-dimensional, or do you ever have, three-dimensional architectural types, like routing through upper or lower layers?
They're mostly 2D. So as I was talking about at the start of the class, we'll talk about interposers later in the course. So kind of 2.5D structures do exist. They don't change the fundamental routing structure of the FPGA, at least at this point. They're really made to make bigger systems than you can make with just one die. And there are some research works where people have looked at truly three-dimensional FPGAs where they stack multiple dice and use through silicon vias. But there are a lot of sort of manufacturability and practicality issues. So I guess the short answer is it's still 2D with a bit beyond 2D enabled by interposers. But truly three-dimensional structures have been proposed but haven't really been manufactured.
Okay, thanks.
You're welcome.